Hey guys, so hopefully last lesson made sense, and that you guys are starting to get a hang of polar notation for vectors. It's really quite a useful notation, um, especially if you go on in physics in the future. Uh, Getting a handle on polar coordinates is really quite useful. There is an alternate representation though, that is also useful, has its place. Mathematically, it's a little easier. It's not going to require a lot of, or not going to require any sine law, cosine law stuff, but it is more work. So that is always the trade-off in math and physics. Um, the easier conceptually will generally mean more math, and the harder conceptually will generally require less math, but it's slightly more complicated. So um, this is the notation you would have seen last year. Um, also called rectangular, with Mr. Morrison. Or whoever you took Physics 11 with if you did it at summer school. But we're looking at vectors in rectangular. It's also called component notation. So I know you've done this before. It shows, especially when you did the projectile motion stuff, splitting things up into X and Y components is effectively what we're going to be doing here. We're not going to call them, well, they are X and Y components, but I do want you guys getting used to this idea of I hats and J hats because it's notation that you're going to use when you go further and study this stuff in university. So a vector can be represented by giving its magnitude and direction. That's polar form. So it's this long and it's this angle. Or you can use what are called components. So we're going to we're going to look at breaking polar form up into rectangular form. For instance, considering the particle and its velocity shown below. So if I have this is the velocity. There's my v, is 5 meters per second. There's my angle. This is north of east. Or you could say that this is above the horizontal. There's a couple different ways you can quote that. This blue vector is in polar form. These two red vectors, though, that I'm going to draw in here, are that polar form or that polar vector in rectangular form. So we can write it like this. So I'm going to just create a little chart here. We're going to have polar, and we're going to have rectangular. Also called component form. Component. So in polar form, this vector is 5 meters per second at 36.9 degrees. And in rectangular or component form, they'll say that's east. And in rectangular form, it's 4 meters per second this way and 3 meters per second that way. We're going to have 4 meters per second east plus 3 meters per second north, or more appropriately, 4 meters per second I hat plus 3 meters per second j hat. This is I hats and j hats that I want you guys to get comfortable with. These are equivalent representations, and we just use regular trig relationships to find these, because these components here, I hat and j hat components, are always perpendicular to each other. That's why they're called rectangular components, because they meet in the 90. In rectangular form, or in component form, we draw the components head to tail. The vector is, or tip to tail rather, that's how I typically, how I typically will word it. The vector is the resultant or the sum of the two components. So if I take, if we want to look here at converting rectangular to polar, this is what it's going to look like. So we're not going to do all of these on one coordinate system. You know what? Why not? Let's do it. Yeah, let's do it. So I need 1, 2, 3, 4, 5, 6, 7, 8. I don't need to go any bigger than 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So there's my coordinate grid. We'll draw all of these on here. Start with this guy here. So if I have negative 3 I hat minus 4 j hat, I start at my origin. Negative 3 I hat, so I'm going left. 1, 2, so I have a vector that's 1, 2, 3 long. There's my negative 3 I hat. Minus 4 j hat, so I'm going to go down. 1, 2, 3, 4. There's my minus 4. There's my minus 3. So then the resultant vector is this guy here. I'll draw him in red. That's going to be 5. Because the 3 squared plus 4 squared equals 5 squared. Or yeah, 3 squared plus 4 squared equals 5 squared. So this is a Pythagorean triple. Should be easy to see what that guy is there. So we just use Pythagoras to figure out, or to do the conversion from component notation to, component notation to polar notation. Actually, you know what? I'll just write that in here. This is the square root of 3 squared plus 4 squared. And then that angle there is just the tan inverse of 4 over 3. That angle is tan inverse of 4/3 is 53.13 degrees. Okay. So now we went from our, in green, we are component notation to our polar form. So this would be a vector of 5, 53.13 degrees south of west. Okay. The conversion is relatively easy. Let's do another one. This guy here. I hat plus 4 j hat. So I hat is going to be 1 this way. If there is no number, it's a 1. And then 4 j hat is going to be 1, 2, 3, 4. So then we've got a vector that looks like this. That's the resultant vector, so we can convert this thing from rectangular to polar relatively easily. This guy's 1, this guy's 4. So this guy here is going to be the square root of 4 squared plus 1 squared. I've done the calculation already. This is going to be 4.12. And this angle in here is 75.96 degrees. So in component notation, we've got I hat plus 4 j hat. In polar notation, we've got 4.12, 75.96 degrees north of east. Let's do the next one. 8 I hat minus 3 j hat. So 8 I hat's going to go out this way. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So there's my 8 I hat minus 3 j hat. It's going to take us down 1, 2, 3. So we got 8 I hat minus 3 j hat. Those are the components. So this guy here is going to be the square root of 8 squared plus 3 squared is 8.54. And this angle right here is, I've done the calculation for us, is 20.55 degrees, and that's going to be south of east. And then the last one here, negative 5 j hat, that's just going to be 1, 2, 3, 4, 5 straight down. So that's negative 5. And because it's not going off at any weird angles, the representation of this guy is the same in polar and in rectangular. So this is just going to, this would just be 5, whatever the units are, south or down or whatever the direction happens to be, or negative 5 j hat. So the conversion between, this is all just examples of converting a rectangular to polar. Hoping relatively straightforward. Flip the page. Changing vectors from one form to another involves simple right trigonometry. It's cosine, sine, and tangent. So if I give you something like this, if we have, again, as always, when we're given something in polar, it's helpful to throw down a little grid, or sorry, a little set of axes, just to help us picture what's going on here. So we can draw it somewhat accurately. Now I want a 20 meters per second, 30 degrees north of west. So I start at west, I go up north 30 degrees. So there's my 20 meter per second vector. So I want to break this thing up into coordinates. What you guys were probably doing last year is you called this thing Vx, you called this thing over here Vy. So this is my right angle there. My x and y components, or my I hat and j hat components, are always perpendicular to each other. We know that this guy right here is 30 degrees. So just long form. If I want Vx, that's adjacent, that's hypotenuse. So cos theta equals adjacent over hypotenuse. I am not going to write it out this way every time. Show you once. And then we'll start doing it long form, or sorry, short form. So this is cos 30 equals Vx over 20. Vx equals 20 cos 30. So that's 17.3 meters per second. And Vy, the same thing, but we're going to use sine because it's opposite that angle. So Vy is going to equal 20 sine 30 is 10 meters per second. So this is how we wrote this thing in polar. In rectangular, we would say that V is equal to 17.3, or sorry, negative, because it's going to the left, 17.3 meters per second I hat, plus, because it's going up, 10 meters per second j hat. Polar, rectangular. And I've done it already a couple times. We'll just do it again. There's a force vector. 5 I hats minus 2 j hat newtons. So let's draw this thing out. 5, again, as always, throw down a little coordinate grid just to make our life a little easier. So 5 I hats, positive I hat means we're going to the right. 5 negative 2 j hat means we're going down. So then our resultant vector is just from the tail of the first to the tip of the second. This is our force vector here. That's going to equal the square root of 5 squared plus 2 squared is the square root of 29. So we got a force vector that's 5.4 newtons. And then to find the direction, we need that angle there. Tan theta is equal to opposite over adjacent, so that's going to be 2 over 5. Theta is the tan inverse of 2/5 is 21.8 degrees south of east. So then we'd say our force vector is 5 I hat minus 2 j hat newtons, or it's 5.4 newtons, 21.8 degrees south of east. That's it. Relatively straightforward, I think, converting between the two. This one you should be more comfortable with because you saw this a lot in Physics 11. You should have seen it a lot in Physics 11. So I'll show you what this looks like when we're adding. We're going to, it says the diagram below, well, we're going to make the diagram below. It's going to show us the addition of two vectors, x's and y's. So let's do it. I got rid of the diagram because it was convoluted to look at. I wanted to draw it out with you guys instead. So here we go. First, we're going to add two vectors together. We're going to do x plus y. Okay. So to do x plus y, we're going to draw x first, and then we're going to put y at the tip of x, add them all together. So x is 5i hat minus, or sorry, 5i hat plus 3j hat. So 5i hat is going to give me 5 to the right. There's my 5i hat, my 3j hats. So my x vector looks like this. We're going to throw down a little coordinate grid right there, or coordinate axes right there, and we're going to draw out the y vector. The y vector is 3i hat minus 2j hat. So again, it's 3 to the right, 1, 2, 3. Minus 2j hat is down 2. So we're going to have a vector that looks like this. And there's x plus y. So we're going to have a vector, a resultant vector that's this green guy here. This green guy is vector x plus y. And we can see what's happening here. To go from the tail of the first to the tip of the second, what I've got to do is just follow these components, right? I've got 5i hats, 3j, and then up 3j hats, and then over 3i hats, and then down 2j hats. Or we could write this thing as, I'll do it in orange here, eight I hat plus j hat. You don't have to write the 1 in there, so I'll just write 8i hat plus j hat. So what I want you guys to see here, the purpose of this exercise is to see that x plus y is the same thing as, so if I had 5i hat plus 3j hat, there's my x vector, plus 3i hat minus 2j hat, I can just group my components like terms. So 5i hats and 3i hats is 8i hats. 3 minus 2 is 1 j hat. Those two and those two. I'm grouping my like terms here. Okay? So that's the power of component notation. We can just sum up the components. Or when you're doing later on in physics, like next year, when you guys are at university, or a couple years, whenever you take this in university, you're going to look at things like cross product and dot product. You're going to be using vector notation there to make those vector multiplications a lot nicer. And so I'm just introducing them now at this point. The fact that we can add vector components as simply as this makes this a lot nicer. Well, it makes the math a lot easier. You've seen this before. We added vectors together. We would have to find what the angle was inside there, and then we'd use sine law or cosine law. Or we can just break things up into components and add the components together. So I don't care how you choose to do them using polar notation or component notation. Those of you who are more mathematically inclined are probably just going to be totally content to do polar notation and tip to tail and using sine law and cosine law. But we can also break these things up into components just as easily. So there's going to be lots of applications of both of these things, and you can choose which of those methods you want to use. Here we go. One more example. This lesson's relatively short. Given K is 5 meters at 10 degrees north of west, and M is 3 meters 30 degrees south of west, we want to find K plus M using components. There we go. Typically how we would do this is we wouldn't draw it out the way I just did in the previous example. what we do is we draw them out separately and figure out what their components are individually. So I've got K, do K and M separately. K is 5 meters, 10 degrees north of west. So it's going to look something like this. So that's 5 meters. That's 10 degrees. And so the components here this one is going to be 5 cos 10, and this one's going to be 5 sine 10. We can call this Kx. We can call this Ky. So Kx is 5 cos 10. Ky is 5 sine 10. I did the calculations for us already. That's going to be 4.92, and the other one's going to be 0.87. So that tells us that vector k in rectangular form is negative 4.92 I hat, because it's to the left, so it's negative I hat, plus 0.87 j hat. It's upwards, so it's positive. Same thing over here. Let's do m. M is 3 meters, 30 degrees south of west. So 30 degrees south of west is going to go this way. This guy's 3 meters. That's 30 degrees. So my components are going to look like that and like that. This is going to, we're going to call that mx. We'll call this guy my. mx and my. mx is going to be 3 cos 30. It's adjacent to that angle. So then my is going to be 3 sine 30. So that's going to be 2.6. That's going to be 1.5. I've done all the math already. So then m, our vector, in component form or in rectangular form, is negative 2.6 I hat minus 1.5 j hat. This guy's to the left, this guy's down, so that's negative I hat and negative j hat. So then if I wanted to write k plus m, that's just negative 4.92 I hat plus 0.87 j hat plus negative 2.6 I hat minus 1.5 j hat. I can rewrite this thing as, so I'm grouping my like terms here, negative 4.92 plus negative, so minus 2.6, that's going to be I hat, plus 0.87 minus 1.5 j hat. Negative 4.92 minus 2.6 is negative 7.52 I hat. 0.87 minus 1.5 is negative 0.63, so I can just write that as minus 0.63 j hat. So that's k plus m in rectangular. So now we want to convert that thing back into polar coordinates. So k plus m is going to equal, let's draw it out just so we have a handle on what's going on here. Negative 7.52 is this way. Negative 7.52 minus 0.63. So k plus m is going to be this blue guy here. And that's the angle we're going to want there. So k plus m is going to be the square root of 7.52 squared plus 0.63 squared, which is 7.55. We need units on that thing. K and m we're both in meters. So k plus m is going to be in meters. And the direction, angle theta, is going to be the tan inverse of 0.63 opposite over adjacent over 7.52 That's 4.9 degrees, and it's south from west. So K plus M is equal to 7.55 meters, 4.9 degrees south of west. Again, the math is much easier. There's no sine law, there's no cosine law, there's no looking at angle relationships, there's no alternate interior angles, you don't need any of that extra mathematical notation. You just need sine, cosine, and tangent, but there's a lot more work involved taking from the beginning. That's it. I'm going to give you some questions to practice this stuff. So flip the page. I want you guys to look at questions. This is page 42. So you guys are going to do 1, 2, 3, 6, and 11. I want to make sure that's everything. 1, 2, lots of conversions there. Sorry. 1, 2, ooh, that's hard to read. There it is, that's easier. 1, 2, 3, 6, and 11. So that's 1, 2, gives you a bunch of things to convert. 3 gives you some stuff to deal with. That's good. Convert both to rectangular, add the convert to polar. It's good. And then I do want you to do 6 and 11. Okay, good. There you go. As always, if you have questions, feel free to ask. I will be here in person Monday to Thursday, or you can hop on to our Google Meets. I saw 9 of you yesterday, I think. I want to remind you that I want to see all of you in person or online at least once a week. So that means there's 11 of you. No, more than that. I saw 9 of you yesterday. That's 20 of you. Oh my gosh, there's 29 of you in this class. 20 of you that I still haven't seen this week. So make sure you either stop in here before you leave to let me know where things are at, or you've got to show up to my Google Meets on Thursday. Good luck.